Welcome to the seminar series organized by GloBIAS.
Everyone to the beginning of our second round of the GloBIAS seminar series. With this talk today, we are inaugurating a new topic that is infrastructure for developing image analysis workflows. Just as a reminder, this seminar will be slightly longer than usual. This is a 2-hour session, and we will record. Actually, we have already started recording the session. If you have any questions, we will address the questions at the end of the talk, and please use the Q&A box on the bottom of the Zoom window to leave your comments and questions, and we will then get them to the speaker. And speaking of the speaker, I will now proceed to present Ank. Ank is he got his Bachelor of Technology in Mechanical Engineering from the Institute of Engineering Science and Technology in West Bengal in India as early as 2021. During his studies, he also co-founded a company dedicated to designing and deploying applications focused on optimizing infrastructure costs. After that, he worked both at EMBL EBI and the University of Cambridge in the UK, developing and building infrastructures for housing and analyzing metagenomics and integrative omics data, as well as working on platforms for processing sensitive data and researching implementation of heterogeneous computing systems, which use multiple computing cores together, like CPUs, GPUs, and others. In 2022, he started working for Ercilia, a nonprofit dedicated to providing open source data science tools for low resource countries, where he collaborated in developing Cyrachem, the first fully automated AI and machine learning virtual screening cascade implemented in a low resource drug discovery center in Africa. Currently, Ank is working as a computational associate at the Carpenter Singh Lab at the Broad Institute of MIT and Harvard in Boston. He works on computational workflows for processing billions of cells in optical pool cell screening experiments. He also created the data and validation and indexing system for the publicly available CellPainting Gallery that houses around 1 petabyte of data generated from cell painting experiments. And the system that Ank created is orders of magnitude faster than the previous version. Finally, Ank will also soon move on to his next challenge and looking for places to do his PhD. So if any of you are interested, and you can contact him after his talk. Today, he's going to give us an overview on the fundamental building blocks for creating carefully designed computing pipelines for dealing with massive amounts of data, drawing examples and lessons from his experience managing and processing datasets from the CellPainting Gallery. So, Ank?
Yeah. Okay. Thanks, Esteban, for the nice introduction. Hello everyone. I'm Ankur. Today we'll be talking about how to process images, lots of them, and hopefully that's something you'll find interesting. So let's just, I guess we can get started, right? Okay. So I divided this talk into 2 different sections. The first section, I'll mostly talk about concept and ideas for decision making, because when you are trying to build such systems, it's usually you're not alone. There are a lot of stakeholders in the project, and you need to make decisions, certain decisions, where the project is going. A lot of the things you have to decide. So I'm going to talk about some of the key concepts and ideas that we used in our own experience and how we manage those. In the second part of the talk, we'll get a little bit technical. We'll talk about the technical challenges we faced along the way while we are building these systems here at the Broad, and some of the potential solutions that we come up with, and you might use these learnings when you'll try to implement such systems in your own organization. So let's move to part 1. But before doing that, I want to set the context here. why we been like why I'm trying to present this topic, and why you might have to think about scaling your pipelines. So here at the Broad, we maintain something called CellPainting Gallery, as Esteban introduced. And in this gallery, we have around 700 terabytes of data, which is reaching a petabyte very soon. And among this data set, we have around 300 million unique objects. If you want to know more detail about the CellPainting Gallery, you can go to this publication we have recently published. You can find all the data sets that are available there. It's completely free to use, and you can use it in your own work. But the thing is, like, we have this CellPainting Gallery, and we have around 1 petabyte of data, but there are no signs of slowing down. The amount of data we are ingesting is kind of increasing exponentially. And I am personally also involved in processing data set from pooled cell painting experiments. And these data sets are massive. An order of magnitude more massive than your normal, cell painting data or any other imaging assays. And we are going to do it more and more here at the pool. So that's why, we started thinking about this problem that right now we have this amount of data, like how this data is going to grow. So we did some, guess estimates and some projections, and with our fairly conservative estimates, we can see that in the next 5 years we'll reach around 100 petabytes of data, and that's not a crazy number. I mean, this is a fairly conservative estimate. It can get even higher. Now, if you look at this problem, right, you have this much amount of data. Our current compute infrastructure, or all the tools we have to process the images, those are not designed to kind of handle this scale. So we internally started thinking about this, and we decided that we have to do something about this, because we don't want to be in a situation where we have all the data sets, but we don't know what to do with it. So we have to think about compute infrastructure. And I'm sure, like, this is not just the case for us. Increasingly, as the technology will become more available, you can see this kind of data growth happening in different areas, in different sectors of biology, as well as throughout the globe. So at some point, you have to think about the compute infrastructure that you'll use to process the data sets. And the one question, the first question you should ask whenever you're trying to kind of answer these questions is, why not go and use existing tools? Because we have very good tools out there right now. For example, we have like SnakeMake, Nextflow, AWS, Workflow Description Language, and many other tools, right? All of them are not, the same kind of tools. They do kind of slightly different things. But these days, I mean, in our current bioimage workflow, we use these tools a lot. These are pretty much, ubiquitous. The question is, can these tools handle the stuff that we are talking about, or we have to do something else? We have to look somewhere else to kind of to make sure that we will still have the capability to process and extract insights from all the data we are generating. So obviously you start here. This is a very valid question, and I'm going to walk you through our own thinking process that we went through to kind of decide that we need kind of our own internal system, which is very custom to our own needs, and we have to build it. So that's part one of this talk. The whole idea behind this decision. And to kind of talk about this, I want to draw your attention towards engineering and design of systems. I won't get into very detailed and depths of this topic, but it's mostly to just give you some idea of how to approach these kind of problems. So let's think about a cup, right? It's a very familiar object that all of us know. So when you think about a cup, maybe you'll think about something like this, right? It's a fairly standard cup. You have a like a vessel which have a cavity, and then you have a handle, to hold it and pour hot liquid into it, and you can use it to drink tea, coffee, like whatever you have. And when you have a cup, you can imagine you have like a lazy Sunday afternoon. You can imagine reading a book, having a tea or coffee, and you're happy, right? So this is the starting place, right? You have a cup of coffee and you're reading a book. Now let's say you went outside, you want to still have a coffee, but you don't have a cup, right? Now you might get your coffee in something like this. It's still pretty usable, right? I mean, you can still hold the container, it won't get burned, you can still drink your coffee. But now let's push it further, right? Maybe, how about this? This is glass. Like technically, you can still drink coffee in it. You can pour hot coffee in it. And if you're careful, you'll be able to hold it. But it's not, I mean, you're starting to break your expectation, right? I mean, this is not a cup. You won't drink coffee in it. Let's maybe push it further. I mean, this is now a bowl. Would you drink coffee in a bowl? I mean, technically you can do it, but why you should do it? And you can take it more further. Maybe it's a pan. It's definitely, this is not the thing you'll imagine when you imagine a coffee cup. So like why this example, right? I mean, why we are going through this? This is to show you, when we move from like a coffee cup to this other vessel, it's like a pan. Technically, we can still use all these things to drink coffee, right? But we don't do that. There are certain affordances there in the coffee cup that makes it, convenient enough that you assign drinking coffee with a cup, right, and not the other tools. So that's the first observation that's very important whenever you're doing any design of a system. Is for humans, design define affordances, and affordances define possible actions. Right. So when you see a cup, right, there's a handle there, right? So that's like a very specific affordance that you built into the design, and that affordance, then defines that, okay, then you can use this tool to drink coffee. So that's like a possible action you attach to a coffee cup, and you can extend this idea to not just everyday objects, but all the systems you use, you build, or that in your daily workflows in your image analysis as well. For example, SnakeMake, right? SnakeMake is an excellent workflow tool. You can use it to define workflows. But is it a bioimage analysis tool? Right? I mean, that's the question, right? You may be able to push it to make it do all those things, but you can start to see that the abstractions will break, and you can start to apply this kind of thinking to a lot of tools you use, and you'll quickly realize the tools you love are specifically designed for the tasks that you are using it for. And as soon as you start to use some tools, and you feel like, okay, I don't think like this is working, or I'm not happy using this tool, then you can quickly point out what the affordances that you want are missing in those tools. So that's like the first thing that you have to understand. That technically a lot of tools out there that can make that you can make it to do the job you want, but that's not the intended design of that system. So that's the first thing. Second is, when we talked about this transition, at each step, we kind of know that, this is a cup, this is not a cup. Nobody's going to say that, for example, I mean, this glass is missing a handle, but you can still pour coffee in it, so it's a 50% cup, right? Or maybe like it's a 10% cup. You don't think in that way, right? Even if you can do those things with certain degree, we don't think in gradients, like continuous gradients, but rather in categories, right? So we have specific categories assigned for each of these objects. And that's something like very unique to, I guess, humans, that we are just hardwired to think in categories. I won't go into like, is it a good thing or like the philosophy behind it? But from a design perspective, this is one of the fundamental statements that you go by, right? That human thinks in categories, and they don't think in like continuous gradients. Why this is important? This is important because if you're building a tool, your users will assign your tool to certain categories, right? And if you try to, try to make like a 10% image analysis tool, that's just not going to work, right? Or like the other way around. Or I mean, not going to work in the sense that it won't be a good user experience. Your users will get frustrated, or like even abandon your tool. So these are like some of the things that you have to think about when you are thinking about design. Okay, and that's why when we were started thinking about the project internally about processing a lot of data set from post CellPainting experiments, we decided to build Starry Night. I mean, we call our pipeline internally Starry Night, and it's a fairly straightforward tool. The idea was like the user can point this tool to their data set. The data set can be either on an S3 bucket or their local files, and then tell the tool some parameters of the experiment, and from there it's all automated. It will take care of like passing the entire data set and generating automatic reports or everything. So this is like the initial idea. Like that was the initial idea we started with. Like we wanted such a tool, but obviously it's not that simple, right? I mean, you have an idea that you want such a tool, and then you'll be like, okay, let's start implementing this. And that journey is in itself, there are so many decisions you have to make. So instead of using this like complicated example, let's simplify things a bit to make this point. So let's think about building a car, right? So not like the entire debate, but for the thought experiment, let's imagine that there are two engineers, and you're talking to them, and you said, build me a car, the best car you can, right? Or like the best car that can exist. And what the engineer like went their ways, started like doing sketches, and the first one arrived, and this is the sketch they came up with. And you started evaluating, right? I mean, you said, okay, I mean, it's aesthetically pleasing. You have wheels. I guess it's good capacity. So I guess it's okay, right? I mean, it looks like a car. Then the second engineer arrived, and the design was something like this, right? Now, I mean, it's technically still a car. You can maybe like drive it. It doesn't look like a car. Not sure what's going on with the wheels. But then, I mean, you cannot say that this is a wrong implementation. Both of the engineers got the same brief, and they arrived at completely different solutions, right? And that happens a lot in engineering. Even if you start with the same brief, you can get in a situation where you are arriving at completely different solutions. Both might still be able to do the things that you ask it to do, but you can clearly see like the person who would ask them to kind of do these designs will select one of those. Well, depending on the person, obviously, like what they're going to select, but they're going to select one of those. What I'm trying to get at is whenever you are trying to engineer a solution, consistent problem definitions are very rare, right? So, and this is usually because of under specification. If you think about the problem we started with, like let's design a car, we haven't really said anything else, right? We haven't said like, you have to have 4 wheels, you have to have like this shape, maybe you have to meet these requirements, all of the things. So there are a lot of assumptions that got built in when you started implementing or like engineering the system. And this is very usual. I mean, this is not something rare. I mean, this happens with every project. Whenever even if you have some idea, you have a good amount of spec around it, and you start implementing it, your solutions diverge. And obviously, with these projects, you're working in a team with different stakeholders, trying to make a consensus around the problem definition is usually one of the key steps for the success of any project. So what I'm trying to say is, whenever you are thinking about, doing this, make sure you have mechanisms inbuilt in your processes to form consensus with all the stakeholders. It cannot be an afterthought. You have to be prepared for it, that this is going to happen. And then you have to figure out, also have a mechanism, how you're going to reach that consensus, what metrics you're going to use, what the process to kind of do that. Going back to Starry Night, we kind of started with the project, right? I wrote a bunch of documentation, did some implementation, we went very deep into the problem, trying to solve it, come up with a system, went back to our stakeholders. In the meeting was basically like, this pipeline is useless for us. It was a longer conversation after that. But what I'm going to say is, like, even if you do all of these things, when you go back to your stakeholders, be open to kind of radical shifts in your approach to your solution, and try to have this consensus forming mechanism inbuilt in your process. So I mean, these are not made up. I mean, these are real life experiences. So these are like two main things that you have to think about when you're designing the systems. When you're designing your systems, first you have to think about what affordances you actually want in your system. So it's basically thinking about your user a lot and your problem space, and then designing your system based on that. And then second, because we're all humans, we work with humans. Be sure that you're gonna have problems getting to a consensus on a problem definition. So have mechanisms to kind of deal with that. So these are mostly for you to kind of navigate the decision-making part of the project. So once you have like done all of these things, you have some consensus, your design space, your users. Now you can start implementing stuff. Right? So the second part is going to be about that, the technical challenges we actually faced, and the solutions we came up with. So just to give you an outline, we'll mostly be talking about these 6 different kind of problem domains. First one is the data management side of things. Obviously, because we're doing a lot of data, we have to manage it. So there are like a lot of things that goes into that. Mostly how you're going to store it, how the data will move, and the permissions that you will associate with your data. The second is we'll talk about then data inventory. It's something that's not often talked about, but in our pipeline, it's a very central piece to make it all work. It's essentially creating a list of all the files we have. We'll go through like how this happens and why we're doing this, and how it can help in your workflows as well. The third is the pipeline itself, which is the configuration of the pipeline, the compute graph itself, take all the functions you have in there, and then the execution backends that you might want to use to actually execute your pipelines. Then you have to think about the reproducibility of a pipeline. Here at the Prod, we at the lab, we are very much deep into this. We want our all our work to be reproducible. And there's like mostly 2 parts to it. Obviously you want to like do open source your code, whatever you're using to do the analysis. A major part is obviously dependency management as well, so that you can actually reproduce. And then other part is the provenance part of it. So the provenance is very, if I have to explain it very simply, think about creating a hash. It's easier to check a hash, than to, it's very easy to then check a hash and recalculate a hash to kind of verify that you are getting the same computation. But again, we'll talk about this in the section. And then the correctness. So think about doing any computation, we have to make sure that it's getting computed correctly. And there are obviously 2 parts to it. Again, we'll delve deep into that section. And finally, performance. Because at huge scales, even if you kind of write code that's like 10% better than the previous one, you're saving a lot of money. So yeah. Okay. This slide, whenever I talk about like engineering or technical challenges or solutions, I often add this as a joke. But this is also a reminder that we were talking about earlier, right? It's too hard to form consensus, and it's very easy to then get into flame wars, right? Which is not my intention. I'm happy to whenever if you have any questions, let me know. But all the solutions I'm going to show you are very much designed for our very custom use case. But I hope like it's kind of general enough that you can use it in your organizations as well. Okay, so the first one is the data management part of it. Our first kind of recommendation, like whenever you're building your systems as a data store, use an object store with permissions controlled through any role-based access control system, and ideally it should be compatible with S3 API. Now there's so many like jargon words here maybe, but what I'm trying to say here is make sure if you're storing data and you want the data to be accessible by a lot of people, try to store it in AWS S3 or systems that are similar to AWS S3. Obviously, AWS S3 is kind of a proprietary solution. You have similar solutions in GCP as well. Or if you want to roll your own, there's open source versions of it as well. For example, Minayo. The question you might be asking, like, why? Why you should use an object store to store your data long term. Compared to what? Like, I mean, compared to storing it on hard drives or maybe a network file system or similar technologies. The answer is the simplicity of an object store. It's just a key value hash, and it's very easy to implement a role-based access control system on top of it. Now, a role-based access control system is, if you ever used AWS, you might get across IAM permissions. It's very complicated, but that's the system, like the theory behind it. If you want to look at it, you can find the Zanzibar paper from Google. But the idea is like it's very theoretically sound. Like most systems these days are converging to role-based access control for managing permissions. So it will become very easy to manage permissions and share files with an object store. And this will become crucial when you start building automated pipelines that needs ad hoc access to your data stores. So that's the first piece, right? I mean, start with an object store. Do not store your files long term in an NFS drive or your local hard drives or something like that. If the data that you're storing there needs to be used or accessed by a lot of people or a lot of automated pipelines. That's the first thing. Second is, if you remember the scale we're talking about, at that scale, any file management operations are not it's not trivial. Even if you have to like copy, delete, or rename across all those files, first of all, it will become very costly. When we did some calculations on our own end on CellPainting Gallery, if we try to even rename files across the entire gallery, it'll cost us around $1,000 just to rename. This is just one operation across the CellPainting Gallery. So you can start thinking about, as the data will scale, these operations will become even more difficult. But that's like even for cost wise, right? I mean, then the next part is like ensuring correctness of the operations. For example, like when you do this kind of operations across objects, you have to do it per object basis. So then, like whenever you are dealing with the systems, often you can encounter timeouts, you can encounter errors in your network, and all those kind of things. So you have to implement your manual handling, batching, retries, errors. So when you're when you in your own laptop, when you press delete on something, it gets deleted. You don't think about it, but that's not the same thing when you're handling with this amount of data. You have to think about error correction and things like that. And then there's also constraints, like other constraints. For example, to even like to do renaming, right? Or any other thing, right? So if you're doing it across this amount of data, either it will take a lot of time, or it will cost you a lot of money. So for example, you can parallelize stuff. So spin up multiple instances, do those operations. It will cost you a lot of money. Or you can just, wait, do it sequentially. They will cost a lot of time. So you have to make those trade-offs, and it will depend on what constraints you are operating in. But you have to think about these things. Let's start thinking about these things. And then next is, once you have, once you figure out how to store data and you are comfortable with doing file operations, the next thing you should usually move towards is having some data schema for your data store. Now, this might be a controversial topic because there are kind of architectures out there that kind of advocates to have a schema-less data lake. They call it data lake, and that's fine. I mean, what I'm proposing is not kind of against it. You can still dump your unstructured data in your data stores, and that's fine. You don't have to do it, by default. But if you want to make automated tools to kind of access your data store and then process data sets on your behalf, then at some point, at some level, you have to introduce some schema, some data schema, so that you can so that the operation can be automated. So even if you're dumping your data without any schema in your data store, so you can think of that as stage 0 of your data layer. Your stage 1 is then you implement a schema on top of it. And when I'm talking about a schema, it's mostly just a list of policies that that will allow to build standardized tooling on top of your data store. So you can think about, you can implement naming conventions. You can implement, if I'm accepting this data set, I need you to upload these files as well, right? That can be a list of metadata or similar files, right? So once you start having this kind of standardization across your data store, then you can build a lot of tools on top of it that can help you maintain data quality as you move along this journey. But one thing to keep in mind whenever you start implementing a data schema is schema should evolve over time. The schemas shouldn't be a static object that you once sat down and decided, that this is what the data is going to look like, and then you never revisit it. You should have like a cadence, for example, like a 6-month or an year cadence where you meet regularly again and again to specifically think about this again. There are multiple reasons to do this because you will never be able to foresee all the data that you are going to ingest. So at some point you have to update your schema to accept new data types, and also the needs might change as well. You might need more structure to build more tools, more automated tools, and other things can happen as well. So you should have this mindset that, okay, I'm building a data schema, but it's going to evolve. So you kind of build your system in a way that your schema is tied to all the systems and is visible. So whenever you're changing anything in your schema, the effects can, in a nice way, percolates to other systems as well. This is not something. This is an important point because often people build the system and then build a schema and then realize, okay, the schema can change, but I have hard coded the schema in a lot of places, and now you have to go back and do a lot of code changes and factoring. So you should be aware that your schema will change. And the last thing, I guess, about the data management side of things is often what I see in the data stores or like S3 buckets is you name your keys of your whatever objects you are storing in a kind of a file system way, right? So this is like hacking a file system on an object store. So what you do is you have this, you make pseudo directories, and that's how you kind of pretend that you have a file system on top of your for example, your S3 bucket, right? It's a very common practice. If you think about it in a more computational, from a computational angle, what you're trying to do is you're trying to represent a tree or you can convert a tree structure into a flat object. This is very suboptimal thing to do, right? And whenever, obviously there are legacy systems, there are a lot of tools that kind of now wants you to have prefixes in your key, and that's how they group files. So we have to maintain that functionality in our system as well. But in any new system we have or that I build, it's discouraged to use or like hack a file system on top of your object storage. You might be asking like, okay, like if we don't do that, then how are you going to group files, or how you even like retrieve files back from the system? And that's the next part, the data inventory section, right? So the idea is like, okay, if the previous solution is suboptimal, what you can do to make data access much easier from your S3 buckets. So it's a kind of a 3-stage thing that we came up with. The first one is you generate a raw inventory. The inventory is just a list of files. So this can be just your object IDs, right? Because we are maintaining a legacy system, so we have these prefixes there inbuilt as well. But you get these kind of keys from your S3 bucket. One quick tip is if you are using AWS S3 a lot, you can ask AWS to generate this inventory for you by default. So it's a free thing that AWS does for you. You just have to like tick some boxes in your AWS S3 bucket, and you can get an inventory every week or every day if you like, even every day if you want. So yeah, that's the first thing. You have to get this inventory. You can also generate this inventory by the methods as well. For example, just doing a recursive ls on your file system. But that's the first step. You get an inventory or like just a list of files. Then you use a parser to parse your keys and convert them to a data frame. So the idea here is, you have this these keys, and then you're converting or extracting all the metadata that's encoded in the key into a standard object, right? And then you can use the final index, you call it index internally, as a data frame to access, filter, whatever you can do with a data frame and get your files that way. Because then at the end, you'll get a list back, and then you can use the AWS tools to download all the files. Or like, if you want to access it, you're even downloading, you can do that. But yeah, so this is why, this is how you can kind of escape not using keys as well, right? Because then you can like directly have an index. Or even if you have a key-based or like a prefix-based bucket already, you can use a parser to convert it to an index, which is essentially a data frame. And then you can do all the data frame operations on it. So we have done it internally at the, internally for the CellPainting Gallery. And these are some of the performances that we see by shifting to this new kind of paradigm. Previously, when we had to, manually do ls to kind of get all our files and then run our validations, because we had a CPG schema before as well. So you're trying to like validate that all the files meet our specification. So this is the old version. We then rewrote it in with Rust and also these parsers, and it's now like 2 orders of magnitude faster than our previous implementation. So this can help us to iterate very quickly. Like now we can iterate very quickly on the schema as well, because we know if we change the schema, we can very quickly validate the schema across the entire CellPainting Gallery. We don't have to like wait a long time to verify that the new thing that we added in the schema is kind of conflicting with the old things or not. So that's the first thing. The second, we also kind of did some benchmarks on just fetching the data, because we already have the index. We don't have to do the recursive ls again and again to know what files are there. And then, I mean, also we can do a bunch of parallel stuff that's usually not happening by default with your AWS CLI. And we, again, like get orders of magnitude faster fetch from S3 as well. So these are like some of the, real gains that we got by implementing these, these tricks to optimize your data management and your data inventory. I just now move to your pipelines. Once we have your data set up, you have your inventory, your index. Now you want to process your images. So when we think about when we started thinking about implementing a pipeline, obviously the first one was these pipelines use a lot of configuration parameters. There's so many functions in them based on different experiment. Based on different, like even the same experiment, but with different batch of data, you might have to like retune your pipelines. So these config files, the configuration of these pipelines are very kind of crucial to get right. How you're managing config is something we thought about a lot. The second part was just the compute graph itself, where you're defining all the functions. We build our own abstractions to that. I'll go to like why we did that. And then finally the backend, right? So once you configure your pipeline, you have your compute graph, and you want to execute it, right? You might want to execute it locally. You might want to execute it on AWS, on GCP, maybe your own HPC clusters. So when we think about pipeline, we think about in these kind of three buckets. So now, if you think about the config part first, right? Usually, I mean, the config files look something like this. This is an example, like a real example from a machine learning experiment, that we're doing for some image processing. There's just so many parameters. Usually, this is the case. And when you look at the code that uses these config files, you always see these branching statements, right? I mean, if this is set, then do this, and then becomes a nightmare because you are doing this kind of nested if-else branching again and again. And you can see this pattern in a lot of different code bases. And it becomes very challenging to maintain such code bases. So what's the solution? I mean, usually when I talk about this, I mean, usually when this is not even acknowledged that this is a problem, or I mean, we can even like improve the situation. But there are like, there are very good patterns, like design patterns that you can use to avoid branching in your code, even if you have very complicated config system. So the idea that you can use is something called composition. So instead of writing these flat config files, you can compose your config files. To explain composition in depth is kind of out of scope for this video. But if you are interested in how this composition in config file works, a very famous repo that kind of uses this idea is Detectron2 from Facebook Research. It's a kind of deep learning based vision models database or like a repository. It's very popular. And they use exactly this model. And this example is from their code base. So this what you're seeing here is actually a config file. But instead of but instead of looking like this, it looks more like function calls, right? And that's how you kind of compose these configs. And then because you're composing configs, then you can write a builder, and then you can avoid all the branching in your code as well. It's a very neat idea. It's hard to kind of express how cool it is, but you have to like write the code yourself to kind of realize that it helps a lot. That's the first thing. If you're writing a config system, try to use this idea of composition in your config files. It will make your life much easier. The second thing is about the pipeline itself. So when we started writing our pipeline, we quickly realized that our needs are very diverse in the sense that we have very different compute environments across different projects. across different collaborators, and they all want to use their own tools to execute the pipelines, right? For example, some of them have already contracts with AWS, and they will only want to use the AWS tools to process the data sets. Some of them are very much invested into Nextflow, and they already have all the infrastructure set up to support Nextflow execution. Some of them love SnakeMake, and they want to deal only with SnakeMake files. Here at the Broad, we also have something called the Data Platform, and they use only workflow description language. So you can submit jobs using workflow description language, and you can think about other tools as well, right? I mean, with AWS, there are other. I mean, they have their own batch scheduler. GCP have something similar. There are other cloud compute vendors as well. So it quickly becomes out of hand, right? I mean, which is the best tool to use? And if you ask this question in your own organization, you might get an answer, right? You might get an answer that, okay, Nextflow is fine, or maybe SnakeMake is fine, or maybe you're only going to use AWS. But for our use case, the answer was we need to somehow support all of them. And this is a major problem, because we don't want to write our pipelines in all these different languages or using all these different technologies. So we came up with an idea which we're internally calling Pipecraft. So the idea was that we have a library in our Python, in the Python environment that you can use to construct an abstract compute graph. And then Pipecraft will work as a compiler, compile it down to different backends. So you give it a compute graph. You can use Python to define a compute graph. You can define what containers to use, what functions to call, stuff like that, all in Python. So you don't have to learn a new language. And then it will create a compute graph out of it. And then based on the backend you'll ask, it will package artifacts and all the backend files for you. So you can generate a SnakeMake file or a Nextflow file, or even you can spin up the entire AWS infrastructure to process your images. This was a major achievement of the project, that we were able to do this. We are still working on it, so it's not kind of out of beta yet, but we are kind of excited about this project. But we kind of did this with our pipelines, is to have this abstract compute graph and then compile it down to different backends. And that's how we achieved compatibility with different backends. And we still have one source code, like a single code base. That was about the pipeline. And then moving towards reproducibility. This is a topic that is close to my heart a lot. I mean, I thought about reproducibility a lot in a lot of different contexts. If you ever worked with Python, you know that dependency management is kind of hell. You're always fighting with managing dependencies, and your journey might look like this, right? You start with just writing scripts, and you realize, okay, maybe you can start using requirements or TXT files. Then maybe you've graduated to Conda, and then you're like, okay, let's just always create a Docker container, and then we can reuse it again and again. Maybe some of you have heard about Nix OS. So we have also been in this journey. Right now, we are very heavy users of Nix internally. And when you think about reproducibility in this context, you have to realize that it's a kind of a spectrum, right? It's not you cannot say like some projects are reproducible or not reproducible. It's always like how much reproducible they are, right? And some are, and you can like set some threshold there and then say, okay, maybe this is a criteria you want. So all of these adds something to your reproducibility story, right? And it's kind of like, if you go this way, the more reproducible your projects become. There are a few key things that I like to point out. Whenever you are working in this space, often people see Docker as the end game, that once you have Docker, have your application Dockerized, that's it, right? But if you if you dig deep, Docker on its own is not reproducible. It's only reusable. So the images you have on Docker Hub, you can reuse it again and again. That's fine. But if you have to recreate those images, it's often not possible unless you were being very careful when you were creating your images. So Docker gives no guarantees, on its own that whatever images you are creating are going to be that you will be able to reproduce in the future, which is often well, depending on your own requirements of reproducibility, can be a big shocker that this is not guaranteed by Docker. So I mean, and that's why we started looking into the solutions. We came across Nix, and Nix kind of gives you that guarantee. But if there's a big caveat there, whenever I talk about Nix to people, I often show this meme always. So what's happening here is do not use Nix if you don't know what you're doing, because it's going to be an uphill battle. It's a very arcane system, but it works. So to give you some context, I mean, Nix was kind of someone's PhD thesis in the 70s or 80s. They wrote about, they thought a lot about how to ship software in a theoretically sound way, that you are shipping the same thing again and again. So there are very strong theoretical guarantees in the system, but it's not easy to use. But if you want, to go all the way and you want to make sure that all your workflows you can independently verify and reproduce again and again, then this is something that we highly recommend. Again, like talking about Nix and why it's useful, how you can use it is out of the scope of this presentation. But I'll highly encourage adventurous people out there to try it out. You might find things that you are missing. Right. So that's the reproducibility story part of things. I mean, in our own workflows, we use Nix a lot. Nix is not just an OS; it's a package manager as well. And it's a cross language package manager. So Python, even C, Rust, all other dependencies, you can use Nix to kind of manage those dependencies, and we use it. Finally, correctness. So when you think about running these pipelines, you want to make sure that it's getting computed correctly, right? And there's two parts to it. The first one is you want syntactic correctness, which is the correctness of computation itself, which is to say that when you multiply 3 times 2, you get the answer 6. You might think this is a trivial thing to do, but it's not. I mean, when you get to floating points, all the rounding stuff that happens, you can get errors in your computation as well. So you have to think about this when you think about correctness, but you also have to think about the semantic correctness part of it, right? Which is to say, it's more about the science, right? I mean, for example, let's say you're segmenting your cells. Is the segmentation correctly happening or not, right? It's kind of a semantic check of your computation. So you need like both of these correctness to happen in your pipelines. And one of the question is, why even like consider this, in this presentation, because this is something maybe trivial. That yes, I mean, correctness is important. We do think about it, but it becomes very important when you are dealing with huge data sets that you cannot reprocess again and again, right? Because like usual workflow, when you think about image analysis, is you load some data and started playing with it. You did some segmentation, it worked or it didn't work. You go back, you do it again, and the cycle continues, right? You can do that interactively with the data sets you have right now. But think about processing terabytes of data. Like you cannot do that interactively, right? You cannot process it and then go back again and process it again. It will incur a lot of cost. So you have to make sure that the algorithms you're using are going to perform, right? And even if it also becomes crucial when you want to do it in an automated fashion. So both of the things you have to think about. So the first part of it, right, the syntactic correctness part of it, you can to kind of ensure this. You can write tests, the usual things. You write your unit tests. You write integration test, end-to-end testing. The next step is you can do fuzzing or property testing for your code base. It is randomly sampling your input space by a fuzzing algorithm. That's how you kind of get a lot of edge cases in your code base. And finally, if you're paranoid and if you want to go the ultimate level, you can actually write computational proofs for your algorithm, and you can use formal proof systems like Lean4 and proof that your computation is going to be correct. This is something that used to happen in the early days of computing, when people when computing was still very much punch cards. So you don't want to spend your time writing code, compiling it, running it, and then realizing, okay, I missed it, like I did a typo. So people did the effort to kind of proof the computation and then then code it. So it's again like tied back to the idea, like if it's cheap, if computation is cheap, then maybe you don't have to think about these things. But if you know that you won't be able to recompute your results again and again, then you have to start thinking about these things. And then the second part of it is the semantic correctness of the analysis. I don't have a good a satisfactory answer to this problem, because it's saying how you can check that your segmentation worked or not. I don't think, if you have the ground truth already, then why you're doing the segmentation in the first place? You can just use the ground truth. But if you don't have the ground truth, you cannot actually check if the segmentation worked or not. You can maybe create some reports and metrics and flag any outliers that you can do. In the same way, you can use some heuristics, randomly sample your outputs and compare it against some expectations you have for results. So these are mostly kind of a random way of getting some checks there. But I don't know what the end game here is. How you can actually make sure that your computation are semantically correct. Yeah, we are still working on it. Maybe some AI algorithms at some point will be much better in these scenarios, but I don't have any concrete answer to that. But it's still something to think about. It's an important thing. If you're trying to automate your systems, you have to think about the semantic correctness part of it as well. And finally, the performance piece, right? You're running so much compute, it better be fast enough, right? You don't want it to be slow. So before doing any performance kind of optimization or thinking about writing better code, always go back and do comprehensive profiling of your entire pipeline. It's very tempting to jump into the code base and figure out, okay, I can optimize this section of it. Let's just spend a month to do that. Go and comprehensively profile your entire pipeline and figure out where your pipeline is spending the most time, and prioritize your performance work in that order, right? This was something we did here internally as well. We use CellProfiler a lot, and we went and for our entire pipeline, we did debugging. We did profiling for the entire pipeline. So you get flame graphs like this, where you can see in which functions how much time we spent. You can do a similar analysis for memory, for your memory as well. But the central idea is comprehensively profile your pipelines before doing any performance optimizations. Here's some other graphs. It's just, yeah, we went very deep into this. Like, I mean, these graphs are mapping out all the function calls that we have in CellProfiler. Just to like, I want to mention that all of this, the work I'm kind of explaining, is not my own work. I mean, I've done a lot of it, but there was a lot of help from other colleagues as well. This particular piece of work is Derman Nodar is our principal software engineer here at the Imaging platform. He's from that Simini lab. But yeah, I mean, so you have to do comprehensive profiling of your current pipelines, and then you have to know your compute. If you want performance out of any system, you have to make sure, or you have to know where it's running. For example, I mean, here internally, we have our own servers that we use a lot, and we know like ins and out of the system. I won't go like into very details of it because it will get very technical. But the idea is, if you're executing your algorithms, let's say on a CPU, you have to know how what the characteristics of your CPU is, how the memory moves in your CPU, how much you can actually move, how many cores you have, because those things matter when you're trying to optimize the system. Again, try to use your accelerators that are specific for specific tasks. For example, if you have GPUs, there are some algorithms that runs very fast on GPUs, but not so much on CPUs. Here in this picture, you have the servers, but this is something called an FPGA. So like one piece of the work, or the entire pipeline we are doing is trying to figure out what compute architectures are best for certain image processing algorithms. And to do that, we can implement a completely new compute architecture. So it's like writing your own CPUs and then testing them if they work better compared to your general purpose CPUs. So I mean, this has already been shown to work very well in genomic space. For example, they use FPGAs to do genome assembly a lot. And there's also a lot of work around compression, and it works a lot better on a very specific kind of compute architecture. But what I'm trying to say here is, right now we are in a very interesting time. We are again entering into the golden era of computing because of the rise of heterogeneous compute. For a long time, we have only used CPUs and maybe GPUs, right? But these days we have NPUs, right? We have other accelerators as well. We have different varieties of FPGAs. So and this will get more and more diverse as we move along. There are new players coming into the space. There will be accelerators specific, designed to do just one task very good. So moving forward, if you want to think about performance, you have to think about the compute you are going to use, and you have to know about those things to get the best performance you can from these systems. So yeah, that's about the compute part. That was mostly what I wanted to talk about. Some like how you design the systems and the technical challenges for it. So usually, when you end up doing these things, you'll have, this kind of mapping where you have some design requirements on one side, and then to fulfill those requirements, you have some engineering implementations on the other side, and then you have this whole stack of abstractions working together with each other, and that's your entire system. I mean, that's how you kind of end up building your systems to process your data sets. So hopefully that was that was useful for all of you. I want to thank my lab first for letting me do all this work. I mean, Anand Shantanu gave me all the independence to kind of research and and think about this problem deeply. I had a lot of interesting conversations with John, with Alan, with Nodar around these topics. So a lot of ideas that you see here are also because of them. And then also Beth and Erin to guide me throughout this journey. They were some of the main, one of the main stakeholders in the project. So we had very interesting discussions around what user experiences you should have in the system. And overall, I mean, thanks to all of you for listening, and I'm happy to take questions.
Thank you, and that was very great talk and very interesting. We have some questions for you. Eric Jelly asks you, the performance improvement are just for getting the file metadata right. The retrieval will be limited by bandwidth anyway, right?
So it will be limited by so there are two bandwidths, right? The bandwidth that you can pull, so your own internal bandwidth, and the bandwidth you can the AWS bandwidth. Usually, you won't be able to saturate the AWS bandwidth. You might be limited by your own bandwidth. But even then, right, we have done multiple experiments here with our own machines. So if you are just using AWS CLI, and if you have a parallel implementation that's running like 100 threads and pulling data from AWS, we usually see better performance with our own parallel implementations compared to just using AWS CLI. Again, it will be limited by your own bandwidth. But if you see that AWS CLI is not saturating your internal bandwidth, then consider trying to shift to a different parallel approach, because that was the case that we were facing. Internally, we had like 1 gigabit connections, but we were never able to saturate that connection with just the AWS CLI.
Thank you. Another question from Amos is say, I guess that Docker is not reproducible since part of the Docker build could require download external resources like packages and etc. that are no longer exist. I didn't understand how Nix OS solved this issue.
Yes. So, okay, that's the first part of the question. It's not just that when you're trying to reproduce a Docker file, the packages are missing. The packages might be missing, and that's the reason you are not able to reproduce. There are other reasons as well. So even if the packages are there, you might be pulling the wrong version of package when you build your image compared to when it was built before. And that will break reproducibility. So that's the first part of it. Now, for the second question, how Nix solves it. So obviously, if the package is no longer there, right, you won't be able to reproduce. But in the Nix setting, what Nix does is it creates hashes of all the dependencies you use in your system, and it stores that, right? So whenever, for example, you get my source code, with the source code, you'll also get the hashes of all the dependencies it used or ever used to kind of run the system or like run the code base. And when you try to pull dependencies again, it will try to match the hashes. And if the hashes won't match, I mean, you'll be sure that you're not getting kind of fake reproducibility, in the sense you'll be able to verify that your system is no longer reproducible, or because of missing packages or a different package under the same name or something like that. So Nix kind of solves it in that way. If the packages are missing, obviously you won't be able to reproduce. In the Docker case, maybe it will pull another version of the package, giving you fake reproducibility. In the Nix world, you are sure that if you're getting the package, then you're getting the same version, or else it will tell you that you won't be able to reproduce the system.
Perfect. Other question is, I have a general question regarding large image datasets. So what kind of image format are suggested for large image dataset? Do you suggest to keep the image in that TIFF format or OMSR formats, for example?
Yeah, I guess, I mean, OMSR is way better than just storing it in a TIFF file format. But there have been, I mean, it's an ongoing discussion in the community. I'll give you, I'll give you a concrete example, like why I'm not just saying that use OMESR, right? So one of the reasons is that OMESR, I guess the spec is still not finalized. So even the creators of OMESR, they are still not sure, they're not still confident, I guess, to recommend it to use in production. You can still use ZAR files, right? If that's what works for you. I mean, ZAR is great. I mean, anything, other than TIFF, these OMESR or like the newer formats are much better. But if you look at CellPainting Gallery, right, we have around 190 terabytes of CSV file. I guess we all know that, CSV files are not great. There are much better formats than just CSV files. So why we still have this in the CellPainting Gallery is, again, comes down to the user experience. We've talked a lot to a lot of biologists, and they still want their CSVs. They don't want to shift to Parquet files. So again, like it will come back to your own your own situation, right? If you can, and all of your users are happy with it, then move to maybe ZAR. That's going to be a much better computational solution. But is it going to be accepted by all your users in terms of user experience? That's you to decide.
Super. Thank you. You mentioned the importance of an evolving schema for the data. Could you elaborate on that? How to initiate it in best practices for its evolution?
Start simple. You do not try to over spec your schema in the start, because you don't know your data, or you don't know the user pattern yet, right? So for example, if you are starting your own CellPainting Gallery from the start, maybe when we talked about schema, yeah, okay. So when we talked about, so if you're starting your own CellPainting Gallery, start with minimal requirements, right? Maybe you'll say you have to have a metadata file with this name, with this format, under the root directory of the dataset, right? Start there and see how and then see like how different datasets start to deviate, right? I mean, they'll start to have single structure, but then start to deviate, and then you'll be like, okay, it diverges enough that now it's creating a problem in my downstream analysis, or like downstream pipelines. So now you have to clamp down. Okay. Then you might add another constraint, right? That you also have to add this, So it's like that. Like the first is start simple. Do not over specify your schema. Keep it as simple as possible. The second part is, I guess it's part of the question, like if you have the schema, it will evolve, how you can manage that in kind of like downstream applications as well. I guess if that's the question, that will depend on so schema. So with schema, there are two things, right? It's the implementation of it in the code base, and then the policy aspect of it. The policy aspect of it is kind of an organization-based thing. So you have to set up practices there, or like regular meetings. The people meet every 6 months, 3 months, like it depends on how fast the data is changing, and they'll decide in some way how to add new things, right? In popular software projects, you might heard of requests for change proposals that people make, that please add this thing to this project because of these things, and they kind of give their reason behind this. So maybe you can set up that kind of process. But again, this is a process. I mean, don't do it at the start. Start with very simple. Make sure that you meet again and again, and start creating these policies at organizational level. So that's the first part of it. For the implementation part of it, it's difficult to explain the kind of code, how you might want to use it. But the idea is like, you have this central repository where you have the schema in some machine readable format, and then you use that as a dependency in your other projects. So whenever the schema changes, your in other code base, you update it as a dependency, and they run all the tests. If something breaks, then you have to change something, but in a way that you are still staying in sync with your schema.
Thank you. Those are the questions. Esteban, I don't know if you want to add something.
No, I think I just have a question regarding the reproducibility. How about the case with log files? Like where would those like fit into your evolution of reproducibility?
Yeah. So you're talking about the requirements.log file?
Yeah, like
Right?
yeah, something like Pixie, like that
Okay.
can like
Yeah.
sort of more than just a requirement.
Yeah. Okay. So when I started thinking about reproducibility, right? I mean, I mentioned it's a spectrum kind of thing, right? Now your question is like where that fits, right? Where the log file fits. And to answer that, you need some kind of metric, right? To answer that question, like and the question is then what the metric can be. And I thought about this, and I'm not sure if this is the right answer, but to me, it looks like the metric have to be how quickly you can recreate or how quickly you can reproduce, right? For example, if it takes, for example, I mean, as you move along this line, the time to reproduce gets shorter and shorter, right? So here, if you're an X, either you'll be able to reproduce, I will flat out say you won't be able to reproduce, right? No matter what. So you don't have to like fiddle with your environment a lot. With requirements or text file, I don't know, maybe you have to change some versions, or I mean, it's been a long time I've used requirement or text file, so I didn't know these days what's happening there. Uh, with Conda, I mean, obviously, usually the NVIDIA drivers are a bit of the problem. If you are using CUDA packages, they usually don't work. So you have to figure out that part, and that takes some time. With Docker, usually it's much better. It usually works. I mean, if you are pulling the containers, if you are trying to rebuild it, it might break. I mean, you don't know, right? I mean, it's up to a lot of different variables. So yeah, I guess so the metric for me is like how quickly I can get to reproduce the same results. Um, I haven't done any surveys, to get that number for you, like where the requirement or text file in compared to like other methods are. Um, but I assume it's at like in this hierarchy, I mean it's at the bottom. And in most cases, if I have to make a call, like to call, like, to kind of make this category of is it reproducible or not, I won't put just recommended text file in the, and say like, is the reproducible project.
Yeah, thank you so much. Yeah, I don't see any more questions coming up. And so if you can go quickly to the last slide, that is the upcoming seminars. Yeah. So thank you everyone for joining us. Just a quick plug. We have our next two seminars for this topic, which will be in the first one in January 22nd on using Nextflow for bioimage analysis, and the speaker will be Chris and Tisher. And then in February 26th, we'll have image analysis using Galaxy by Beatrix Serrano Solano. You're more than welcome to come and invite others. And I hope you enjoyed our seminar. Krista, do you have anything else to add?
No, everything is fine. Thanks a lot for this fantastic presentation and for everybody organizing this. And I hope everyone enjoyed it.
Yeah. Thank you so much, Ank, for your talk.
Yeah.
Thank you,
Thanks,
Ankur.
everyone.
Yeah. See you next time, everyone.
Bye.
Bye.